In this section, we're not going to be learning anything new. We're going to review some of the exponentials that we did a while back, and we're going to learn how to apply the logarithm stuff we just learned to solving these exponentials. So first, for a review, we started out trying to solve problems that looked like this, and we said, well, if you have two exponentials that have the same base, you can set up an equation pretty easily. Now, these do not have the same base, but it was quite easily to convert 25 to 5 squared. Then we do have matching bases, and we can just set those exponents equal to each other and then solve. So we subtract 10 from each side, and we got 9 is equal to, n is equal to negative 8. For this problem, we looked at our two bases, 9 and 27, and we said, well, they have a common root of 3. So we are going to rewrite 9 as 3 squared with that a plus 2. And we're going to rewrite 27 as 3 to the third at 4a minus 2. And here's our equation. 2 times a plus 2 is equal to 3 times 4a minus 2. And then to solve the equation, you distribute into both sets of parentheses. So you're going to have 2a plus 4 equals 12a minus 2. 3 times 2 is 6. Then we're going to subtract 2a from each side. So you get 4 is equal to 10a minus 6. Then you would add 6 to each side. This is just your linear equation solving. So now you have 10 equals 10a. Divide both sides by 10. And you get 1 is equal to a. Naturally, you can fill it in and check. Alright, next let's move into what happens if you don't have matching bases. Now to move forward into some application, I have the same problem written twice here. This is an exponential problem. I have a numerical base with a variable exponent. So, one of the possibilities, since I can't change 61 to 2 to the something power so that I have matching bases, then I would solve it like we just did the other two. I go to one of these two options, and the first option, remember your goal when you solve an equation is to isolate this variable. Right now I don't have any way to get that exponent down from there. But here's a trick. If I rewrite it as log 2 to the x power, and I do the same thing to the other side, still balanced, now I can take this, I can move the x over here using your power property. So now I have x times log 2 equals log 61. Still trying to isolate this variable. It's been multiplied by log 2. So I'm going to divide it by log 2. And I have x equals, and if you look, this is your change of base right here. So all you have to do is put that in your calculator as log 61 divided by log of 2, and you get x is equal to 5.9307. Now let's look at method 2. We can take this exponential and we can rewrite it using our conversions from a couple of lessons ago. We learned how to take an exponential and rewrite it as a log, and we did that by log of base 2, remember, and then we swung over here, of 61 equals x. Now, at this point, if you have a calculator that has the capability of doing other logs, you can just put that in your calculator. Since I'm using the calculator that only does base 10 logs, I'm going to do my change of base, which means I've got log 61 over log 2 equals x, and that's actually what we evaluated right here. So if I punch in log 61 divided by log 2, I'm going to get 5.93 9307, just like I did here, okay? So two different ways to attack it, but you still wind up with the same thing towards the end. All right, let's look at some more examples. Now remember, this is nothing new other than it's a new application of the stuff we've already been learning, so just watch and practice. That's all I can tell you. The more of them you do, the better you're going to get at it. Okay, so here's an exponential problem. How do I know it's an exponential problem? What is an exponential? It has a numerical base, a constant base, and a variable exponent. So, I know I can either use log to log or I can rewrite it as a logarithm to a number. I'm going to go with that method. So this is going to be log base. What's your base up here? It stays your base. And then you swing over here of 8 equals x. And once again, if you have a calculator that has the capability for an odd log, you just put it in there and evaluate it. Since I don't have that, I'm going to use change of base, and this is going to be log of 8 over log 12 equals x. And let me put that in the calculator real quick. I've got log 8 divided by log 12, and I get x is equal to 0.8368. Let's do another one. Once again, analysis. Exponential problem because I have a constant base and a variable exponent. I'm going to go with my converting a log into a log. So I have log of, here's your base 8, swing over here to 92 equals x minus 7. Now, let's evaluate this in the calculator. Once again, going to my change of base. So I have log of my argument over log of my base. And real quick, that's going to get me 92 divided by 8 is 2.1745. Let's go to 4 decimal places. And then I have the x minus 7 here. So now, in order to actually solve the problem, I have to add 7 to each side. So I get x is equal to 9.1745. Okay, let's look at another problem. I've got 4 times 7 to the n power is equal to 148. I see my exponential right here, 7 to the nth power. When you get ready to solve an equation, you want to isolate the variable as much as possible. So I can easily divide both sides by 4 here, and I get 7 to the nth power is equal to 148 divided by 4, 37. Alright, now I have an exponential to a number, so you can either do log to log, or we can do the log conversion. I'm going to do log base 7, swing over here, that makes my argument equals my exponent, okay? And once again, if you have a good calculator that does all bases, you can punch that in and get your n. But since I'm having to do change of base on all these, my n is going to be equal to log of my argument over log of my base. So I'm going to do 37 log divided by 7 log equals, n is equal to 1.8556. Okay, let's look at this next problem. I've got 7 minus 4 to the x plus 1 is equal to 18. I need to isolate the variable as much as possible. So the first thing I'm going to do is subtract 7 from each side. This gives me negative 4 to the x plus 1 is equal to 11. I also want to get rid of that negative sign. So I can multiply both sides, or I know some of you like to divide. Multiply or divide by negative 1. So now I have positive 4 to the x plus 1 is equal to negative 11. And I'm going to convert this to a logarithm by doing log, this is my base 4 I'm going to swing over here of negative 11 equals x plus 1. And I can stop right here. This one has no solution. Do you remember why? Because you cannot have a negative logarithm. Remember, the domain of your log is that x, your argument, has to be greater than 0. It has to be positive. So this is a no solution problem, but it did let you see the technique. So here we are, 4 times 3 to the n plus 15 is equal to 359. So, just like solving a regular equation, let's isolate the part that has the variable first. And you get rid of the number that's added to or subtracted from first. So I'm going to subtract 15 from each side, and this is going to give me 4 times 3 to the nth power is equal to 344. Next, I'm going to divide both sides by 4. So I get 3 to the nth power is equal to, I'm going to calculate that one, 344 divided by 4 is 86. I have a true exponential now. So I'm going to go to my logarithm. It's going to be log base of 3, swing over here to the 86 equals n. And let me do my change of base formula. I've got log of 86 over log of 3, and that's a calculator problem there. So 86 log divided by 3 log equals, n is equal to 4.0545. Okay? Practice, guys. This just takes practice. It takes doing a lot of them. So I want you to work the rest of the ones in your guided notes and the ones in the homework worksheet. Let me know if you have any trouble.